everybody, today we're going to learn a little bit about mass spectroscopy. A quick review about isotopes. An isotope is an atom of an element that has a different mass number. Since protons are unique for each individual element, this means that the only other subatomic particle that contributes significant mass, aka the neutron, is the particle that there will be different amounts of. For example, carbon-12 and carbon-14 are both isotopes of carbon. So you should consider how many protons does each have and how many neutrons does each have. Since carbon is atomic number 6, both carbon-12 and carbon-14 have 6 protons. However, they have different mass numbers. So in order to determine the number of neutrons, we would take the mass number for each isotope and subtract 6 from it. So for carbon-12, 12 minus 6 equals 6. That means carbon-12 has 6 neutrons in its nucleus. Meanwhile, for carbon-14, 14 minus 6 equals 8. That means there would be 8 neutrons in the nucleus of a carbon-14 atom. Another thing we need to review is average atomic mass. On the periodic table, you'll notice that I don't have whole number masses listed. Rather, I have a decimal one, for most elements at least. This is the average atomic mass for the element. It is a weighted average. For a weighted average, what you generally do is you take a percent contribution in its decimal form, or a weight for each thing, multiply it by its weight, and then add all the individual pieces. For example, consider your semester grades are a weighted average. They are an average of your 2 quarter grades and the final exam grade for that semester. Specifically, the weights for each are 40% quarter 1, 40% quarter 2, and 20% the exam grade. This means that quarter 1 and quarter 2 contribute more to your grade because they have higher weights. Let's do an example of how to calculate average atomic mass to review this skill. Calculate the average atomic mass of silicon. It has 3 isotopes, silicon 28, 29, and 30, and their relative abundances are provided as well. So what we will do is we will take each of these isotopes, number 28, number 29, and number 30, and multiply them by their respective percent abundances. However, the percents should be in their decimal form. So for silicon 28, we will be multiplying it by 0.922279, which is 92.2297% in its decimal form. So let's set up our work. The average mass will be equal to 0.922297 times 28 plus 0.046832 times 29 plus 0.030872 times 30. When I multiply these out and add up the pieces, the result is that the average mass for silicon is 28.11 AMUs, which is very close to what is reported on the periodic table. The question then is, how do we get these weights, the percent abundances? The weights that we use are the percent abundances. They are the relative amount of each isotope present in a sample. Generally, to have a more accurate one that reflects the periodic table, you will want to have a larger sample or a sample that you know accurately reflects how it generally behaves in nature. Percent abundances must be experimentally determined using what we call mass spectrometry or mass spectroscopy. The instrument that's used for mass spectroscopy has a general outline here in the image. The general process is that you place a sample inside the instrument. The sample then runs into a source where it will be ionized by some energy. Specifically, the energy that is applied is usually sufficient just to create a +1 cation. If too much energy is supplied, you might get a +2 or +3 cation. So be careful, but generally you just want to apply the amount for a +1 cation. Then it is sent into a tube area where the ions become accelerated so that they move quickly. Then, as they continue out of the accelerator, they approach an area where there is a magnet. Because these are cations, they will react to a magnetic field and their path will bend in the magnetic field. You'll notice there's a note here that the more massive the ion is, the less it will bend. Consider which is easier to bring to a stop, your own car or a semi-truck. Your car is easier because it has a smaller mass. Things with smaller mass require a little less force to be bent out into a different direction. So more massive ones will bend less. They are more on the top of the image that's shown, and the less massive ones will bend a lot more. They're more shown in the bottom rays. Then, once they have been bent and separated, they will go into a detector area. The detector will catch the ions. It will note location, which will correspond to the mass, and will also note frequency, which will correspond to the percent abundance. So let's look at what the results we get from the instrument are. The instrument interprets the data and returns to you a graph that looks very similar to the one shown here. A mass spectrum is the graph you're going to get. On the x-axis, you will find the mass-to-charge ratio. Usually this is often simplified to just mass, since the charge is usually +1. So it would be mass divided by 1, which just leaves the mass. On the y-axis, you will find various labels. Generally, it's something like percent abundance, intensity, count, relative abundance, etc. Basically, the y-axis is something that counts how often there was a collision for that particular isotope. You'll notice here, this particular graph has it as intensity in percent abundance, which is convenient because the percent is the form we will need to move forward with our calculations. Things you might be asked to analyze regarding a mass spectrum. You might be asked to consider which isotope is the most abundant for what you collected data for, or conversely, which one is the least abundant. You might be asked to calculate the average mass for the element, or you might be asked which element spectrum is shown. So let's work through how you would determine the answer for each of these prompts. If you were trying to determine simply which isotope is the most or least abundant, you are looking at the peak heights. Ideally, the numbers for the heights should be listed as they are in this graph. So for example, I know that the isotope number 24, which has a height of 82.8%, is the most abundant because that is the tallest peak that is shown. Conversely, I know that isotope number 25, with a percent abundance of 8.1%, is the least abundant because it is the shortest. You may also be asked to calculate the average mass for this element. In this case, you're simply going to perform an average atomic mass calculation using the percents and the masses that are located on the graph. So for example, isotope number 26 has a percent abundance of 9.1%. So for that segment, you would take 26 and multiply it by 0.091. Be very careful. If your y-axis does not list in percent abundances, that means you do have an interim step you must do of determining the percent abundances first. In those cases, what you will likely have is a relative count. For that, you'll have to add up all the relative counts, and then for each one, take the count you had and divide it by the total, and then turn it into a percent. Again, this particular graph does not require that because it is already in percent abundance. And finally, let's work through a problem. Which element spectrum is shown? In order to determine this, you will have to calculate the average atomic mass. So let's lay out our work. The average mass will be equal to 0.828 times 24 plus 0.081 times 25 plus 0.091 times 26. So each of the percents turned into its decimal form times the isotope. We will then multiply each piece and then add them all together and get that the average mass for the sample is 24.263 atomic mass units. Now, in order to determine which element the spectrum belongs to, we should have a periodic table handy and look for an element whose average atomic mass that is listed is closest to the one we calculated. That would imply that this is a sample of that element. Note, it might not be exact because perhaps the sample doesn't quite mirror everything that's in nature, and therefore it might be slightly off of the one on the periodic table. So, since the average atomic mass we calculated was 24.263 mu, and magnesium is the element that has the closest reported one at 24.31, the sample was likely a sample of magnesium.